Today, we want to revisit the question about what's calculus. We want to think about upgrading our calculus thinking to work in higher dimensions. Notice that this semester, we have not really talked about the calculus ideas, the big calculus ideas of change, continuous change. We have not talked about the two big operations, derivatives and integrals. We have just been describing stuff. So what we need to do now we've taken a couple of weeks to describe some stuff, we need to start implementing some calculus thinking. To do that, we're going to remind ourselves of the categories of calculus thinking. So this is what I specifically mean when I say our calculus thinking. Back in Calc 1 and Calc 2, we would consider functions of one variable to make our lives easy. These one-dimensional curves in R2, and we would ask two questions. Number one, what is the slope of the line tangent to the curve at a given point? And number two, what is the area under the curve and above an interval on the x-axis? So recall the two big questions. First, I want the alphabet. People taking notes in pen are like, dude, I can't erase. Yeah, you know what? The two big questions that we were concerned with, the first one was what is the slope of the line tangent to the curve at a given point? And the other one, the other question, I didn't space this very well. This is the framework where we study continuous change. This is the framework that we use to study continuous change, which is what calculus is about. I do want to make one small modification. So this is, I did what is the slope of the line tangent to the curve at this point. I want to upgrade this so it would help with our thinking. What is the equation of the line tangent to the curve at the given point? Specifically, I want it crossed out like that with the equation written above to remind ourselves that the thing we were looking for is slope. Any questions? So the other thing I want to specifically do, the reason I want to write this down is that I want to make sure that we don't just say area under the curve, but specifically, we are looking for the area under the curve and above an interval. We're looking for the slope of the tangent, the equation of a tangent line, and then we're looking for the area under a curve and above an interval. So we're looking for the equation of this line. And we're looking for the area under the curve. So the second problem. This was the framework. Then we looked at, for which we studied continuous change. And we learned some mechanics to do this quickly. We want to be able to do this quickly, and that's what we had mechanics for. For the first question, what were our mechanics? How do we get the slope of the line tangent to the curve? What operation do we use? What is it that we need? I want the equation of a line, so I'm going to say y is equal to y naught plus m times x minus x naught. How do we get the slope in this case? Derivative. We take the derivative and plug in the point that we care about. So the slope is f prime at x naught. How do we find the area under the curve, 4 minus x squared, and above the interval from -1 to 2? What object do we use for there? What operation do we use here? We integrate. We use specifically the definite integral. So the area is the definite integral from -1 to 2 of the function. I'm just going to write it in context. The definite integral of the function over the interval. There's a lot that goes into this. Considering our discussion today, we care about this 4 minus x squared. That's the height. And then the width is the delta x, or the dx. And we do that calculation at all the points x. Remember that the only area that we need is length times width. The only formula for area that we ever need is the idea of area, length times width. So what this definite integral is telling us to do is multiply length times width at all these x values. So this comes from length times width at all these x values. It's a little bit weird to say we're adding up all these length times width because we're adding up over a continuum and there's nowhere to put the plus sign. But that's why we have the Riemann sum that leads to this. The Riemann sum is the discrete version with all the plus signs. Then we just get more and more plus signs. And then we just use our imaginations and our technology of limits to think what would happen if we just did this continuously. There's nowhere to put the plus signs, but that's the way we're going to think about it. Our length, we're just adding up all these lengths over these infinitely thin widths. Here's what we want to think about today. This is what y'all are going to be discussing today. We are going to do the same thing, but with one of our new objects. We always start off with functions to make our life easy. If we require one variable to be a function of the other variables, that makes the structure easy. Each input will have exactly one output. Life is much better. But now we're going to be considering the function z, which will be a function of x and y. Here's my function of x and y. When you look at this function, you should think, dude, that is the same function you used in the previous example. Yeah, yes. Yes, I know. That's the point. But here's my question. Oh, first of all, now we're dealing with a two-dimensional surface in R3. So I've gone from asking the questions about a one-dimensional curve in R2 to a two-dimensional surface in R3. And this is what we're thinking about today. What do the two big questions look like when applied to this function? I want you to think about what do the two big questions look like when we apply them to this function of two variables. How can we modify the two big questions? Remember, this is Calc 3. The calculus thinking is still the same. We're modifying we're just modifying the function. I'll give you a moment now to gather your thoughts. Then we are going to get into groups and you're going to try some stuff. Class hasn't been awkward for a while, so we're going to be getting into random groups. I don't know why I cut the cards. I shuffled them up and then because they're all grouped like I don't even know why I bothered with that, but I shuffled them up and then I cut them. Weird. Okay, so you have to talk between a job and your what? Still number 3. All right, so I want you to think about how you would modify the two big questions. to fit this function? What has to change so that we take our function of one variable and now we're dealing with in a function of one variable to a function of two variables? What kinds of things have to change in our two big questions? All right, let's pause the recording. Go ahead, gather up in your groups at the appropriate boards and discuss. The two things that we were thinking about and the way that these are the same questions and the way that they're going to be different questions. In the first one, we're looking for a linear equation. In two variables, a linear equation produces a line. What does a linear equation produce in three variables? A plane. So instead of a tangent line, we're going to find a tangent plane. So yeah, we'll have an equation instead of y equals y naught with one slope and a point, we'll have a point and two slopes. That's how we were thinking about planes in the first place. Then vectors jumped in and said, hey, make a normal, but that's not what we're seeing here. In the other one, in the other question, what is the area under the curve and above an interval? So we have an area under a curve and above an interval. The function acts as the height or the length, and the interval is the width, giving us an area, length times width. How many do we need to make, oh, I guess I can't say the next part. What changes in this question when we upgrade to a function of two variables? What word changes?
Area to volume.
Area becomes a volume. So how many dimensions do we need to make a volume? 3. We need 3 dimensions to make a volume. We've got one of them described by the function in the same way as that we had height described in area. Height in the function is the function. So I need 2 more. I've got one height, which is given by the function. So I need some x's and some y's. So we're going to have the volume under the surface and above some region in the xy plane. That's where things get more interesting. Intervals as subsets of the x-axis, very boring. Start at A, end at B. That's all you can do. Nothing else is, you just can't do anything interesting with an interval. Start, end, done. But with a two-dimensional region, we bring in the complication of shape. We could just do x from A to B, y from C to D and make a rectangle. But in 2 dimensions, we can make all kinds of shapes. In particular, this surface, when it intersects the xy plane, what is the shape that it's sitting above? It's sitting above a whole circle. And we could divide that circle up. Maybe instead of that whole circle, we just want a rectangular part of that circle. The complication that we're going to have to deal with in future is describing a region in R2 is more complicated than describing an interval in R1. Any questions? Right. These questions will come up later. We're just doing inception today. So that could be sitting in the back of your mind. Tormenting you as you figure out what the dx is going to become. All right, that's it for today. I will see you all on tomorrow. Please bring up your cards. Make sure you sign in on the sign-in sheets. Have a good day and thanks for playing.